What's up, guys? Welcome back. Episode 97 today, I think. Let's take a look. Yeah, we did 96 yesterday. Yeah, drowsy. Today is a hypno. Let's check out the sound. Jesus, man, that's a hard one. How's that sound, man? There's our sound of the day. Hypno. Let's go. Let's take a look at our Leetcode problems. We looked at this one yesterday. I believe what we're going to do is we're going to look at some tries. We did heaps. Maybe we might look at another heap problem today. Advanced graphs, mean cost of all points. I think what we'll do, we'll look at a shit ton of backtracking problems, man. I think that's the goal for today. I think we've done a lot of these. You know, maybe just to reinforce that recursion knowledge, the backtracking too is definitely important. Combination sum. Okay, we'll take a look at this problem, but I'll be back in a second. I gotta quickly do something. 1 second. My Spotify's down, but that's okay. Let's take a look. Combination sum given an array of distinct integers candidates at a target and a target integer. Target return a list of all combinations of candidates where the chosen numbers sum to target. You may return the combination in any order. The same number may be chosen from candidates an unlimited number of times. Two combinations are unique if the frequency of at least one of the chosen numbers is different. When did we do this problem? Jan 20th. Candidates 2, 3, 6, 7. Target is 7. Okay, so I think we're adding up to the target. Okay. So I think we create a reservoir. We define our backtracking function. We probably want to start passing our starting index and our cur, right? Or, sorry, our starting index and our cur. Call our backtracking function. Backtracking, passing our index, which would be 0, is our starting value, and our cur. Oh, our cur right now, I guess, is an empty string. But our base case here, well, I feel like it's pretty obvious when our target reaches 7, right? So if the sum of cur is equal to 7, can we use the sum function on the list though? Can you use sum on the list? I'm pretty sure you can. Okay. Then we would just want to do, well, res.append cur copy. We would return, right? Our recursive case would be, okay, we'd want to increment by 1. So we would want to go, okay, well, cur.append append our index, and then we'd want to call our DFS function backtracking increment our index plus 1. Now cur dot pop, backtracking, index. I think it'd still be index plus 1. Cur. Turn our res. Backtracking is not defined. Backtrack. Backtrack isn't. I saw a shadow flying high. He came to me with the sweetest song. Peter Pan, that's what they call me. Why is this not working? Oh, it was equal to 7. Oh my god, target. Jeez. Will that work as a base case though? Because technically we can keep adding numbers, right? Like, the list of all unique combinations of candidates. Passing our backtracking function. What are we going to do first? We're going to append code or append index, right? We're going to append 2. Then we're going to call backtracking index plus 1. We're going to come over here. We're going to check our sum is equal to target. Well, no, it's not. It's 2, right? So we're going to go back here and we're going to index plus 1. We're going to add 3. Oh, we can add duplicates. Okay. Same number may be chosen from candidates an unlimited number of times. Given an array of distinct integer candidates and a target integer target, return a list of all unique combinations of candidates with a chosen number sum to target. You may return the combinations in any order. The same number may be chosen from candidates an unlimited number of times. 2 combinations are unique if the frequency of at least one of the chosen numbers is different. Test case is generated such that the number of unique combinations that sum up to target is less than 150 combinations for the given input. Sum is equal, cur is equal to target. Well, it could be go above cur, so maybe we need 2 base cases, right? think that's why we're getting the timeout, right? So if the sum of cur is greater than target, what will we do? We just return, right? Maximum depth exceeded. The recursive case. I know if we have our sum current it's equal to target, we need to append to the res and return. I know that. But if we add up all these values and it goes higher than let's take a look. Okay, I just realized I'm not actually adding the index. The value. Candidate's index. Cut order pan candidates index. Backtracking index +1. I know this because we're going out of bounds in the index, but yeah, X out of bounds. And then code.pop index +1. Okay. This index is out of range. If index is less than or equal to the length of candidates do we have to put them both inside the if? Apart from empty list. To the length of candidates -1. I'm popping from empty list now. No way that worked, bro. Bro, how did that work? I still don't even know how that worked. We're checking the index here, then we're appending cur. We're backtracking the current value in our index, right? If it's greater than target, we return nothing. If it's equal to the target, we append. Is this how we did it last time then? Jeez, we did it a little different. Avoids duplicates. I don't think there is any duplicates in the question, bro. Yeah, I don't think there is any duplicates, bro, in the question. Wait, description. I swear to God, they said. I swear to God, it says somewhere that is distinct, given an array of distinct integers. Piss me off that Spotify is down. I cannot even log in. What do we do here? We did backtrack base case. Okay, we take the current sum is equal to sum of stop unnecessary request. If current sum is greater than target, we return. If current sum is equal, we append to our request case for J in start to length. Code or append candidates J, backtrack J, we pop. Spotify, dude. Okay, interesting problem. Let's take a look at the next one. Combination sum 2. Combination sum 2. We have completed it. We did this Jan 26. Okay, given a collection of candidates and a target number target, find all unique combinations in candidates where the candidates number is summed to target. Each number of candidates may only be used in the once in the combination. Note the solution set must not contain duplicate combinators. Okay. All unique combinations in candidates where the candidate number is summed to target. Low key. Oh. Okay. Obviously we need a res array. We need def backtrack. Let's put in our index and our cur, right? We're gonna backtrack here. Call the backtracking function, pass in 0 and our cur, which is just an empty array. We're gonna return our res, right? What is our base case? Well, our base case will be, I think, the same as the last one, right? If our target, if the sum of our cur is greater than target, we just return. The sum of our cur is equal to target, then we can append the copy, cur.copy, and we return, obviously, right? We have our recursive case now, where, okay, we want to loop through each of these values. 1, 2, not contain duplicate. Do the same thing. Well, if the index is less than or equal to the length of candidates minus 1, And what do we want to do? Well, we want to probably append cur.append candidates 0. We don't include, given a collection of candidate numbers, candidates and target, find all unique combination candidates with the candidate's number of sums to target. Each number and candidates may only be used once in the combination. Each number in okay. Candidate 0, then we probably want to backtrack. So we go backtrack. I feel like we probably do it the same way as the previous one, right? Because we don't want to include duplicates, but we still want to backtrack, right? So maybe we'd pop here and we call our backtracking function again on index +1. Okay. Let's see what that gives us. Okay, we're not appending anything. Backtrack. Oh my god, candidates. Index. Okay. We're getting somewhere. We have 161, which is this one here. 125, which is here. 17, which is here. And then 26, which is here. But we already have 215, and we already have 71. So now what we have to do is we have to figure out a way, okay, how do we know if it's a duplicate? Set must not contain duplicates. I don't think we can use a set here because can you hold lists inside of a set Python? I know you can, but I don't think the cannot directly hold lists because lists are mutable. They're changeable, and set elements must be immutable. Immutable, but we can put it in as a tuple though. Maybe that's a play here. Could be. Let's try that. Let's try and insert it as a tuple. Is this? I might be cooking here. So we put hashy is equal to set, right? We do set. We would do hashy.add cur.copy. Hashy.add tuple cur.copy. Am I cooking here, right? And then we would return the list version of the hashy. Am I straight cooking here? I don't know. Maybe I'm not cooking now. let's do like cur sorted cur is equal to cur dot sort. And then we do sorted cur equals sorted cur dot. I don't think we need the dot copy, bro. Sorted cur. Object is not iterable. Why the... Maybe we just need to do cur dot sort and then cur dot I don't know if I'm cooking here, bro, but the time complexity is going to be insane, though. Like, I think this will submit, but the time complexity is going to be insane. Like, as we're sorting inside of here, we're summing, well, it's not going to submit. Yeah. Yeah. What is this time complexity? This is... Of 2 and 1 is number of candidates. Yeah, we're like... Worst case time complexity is of 2n times n log n. Total recursive branches 2n and log n sorting cur to store it in a set. Yeah, we're gonna have to... Res equal to this. Let's get rid of the tuple. Just put code.copy. Alright, we return. You change this to a res.append. Turn res. How can we do this? Can we sort before? Can we do, well, candidates dot sort? Two 5 1 7. We got a 1 2 5 already. We have a 1 7 already, and we have a 2 6. Okay, this might help us here, right? Well, if... Oh, no, we have a code sort here. Let's get rid of that. Okay. Maybe now we can have this as a set. Hashi is equal to set. Right, and we just append hashi.append. We append the tuple version of this copy. We would return the list version of the hashi. Will this work now? Now that we sorted it outside of our function. We're going to append. We need an add here. Will this submit now? Nope. Oh my god, dude. Why am I getting a TLE? I think maybe we gotta figure out this sum cur Three main issues: repeated some curl calls. Okay, no pruning / duplicate skipping. Even though you sort candidates, you're still exploring every subset without skipping duplicates intelligently. This leads to exponential redundant branches. You're relying on a set to eliminate duplicates after the fact, but you can avoid generating them in the first place with better control. Okay. Okay, looks like Spotify's back up. Logging me in, dude. Okay, guys, I'll be back in 1 second. Okay, we're back. Sorry, I had to log in by Spotify. I just needed to play with it for a couple minutes, but we got it working. Now we got to figure out this TLE issue. Instead of taking the sum of cur, I feel like we can keep track of the... Can we keep track of the... We can keep track of the length, right? Passing the length here. And add, we can do length plus... No, it's not going to work. Because how do we keep track of the pop, though? Because we're just popping from the end. Unless we could do like last element is equal to cur.pop. And then we can do, okay, well, the length minus or equal to last element. Do this, because then we can do, well, length minus or equal to plus or equal to cur. Sorry. Candidates index. Then can we do, okay, well, if the length is greater than target and the length is equal to target, will this run? Invalid syntax. Is it just plus? This sort of pen takes exactly one argument, 2 given. Oh shit, dude. I did it in the wrong spot. Okay, that doesn't work. Let's get rid of this length. Sum of cur. Sum of cur. Oh shit. And I was on far away, and I'll someday. Nobody knows. Nobody knows. I was dancing in the rain. Okay, let's put in this. How can I? What's there? Repeated sum calls duplicate of one is efficient. Using a set of tuples is okay, but we can do better using in-place duplicate sorting. Results variable. We have a path sum. Path sum is equal to target. We append cur. So it's greater to target we return. For I in range start to the length of candidates, we skip the derivative. If I is greater than star. Drag I plus 1 cur path sum plus candidates I. Dot pop return index or value. Okay, just want to make sure. Okay. Let's move cart total in here, right? 0. Move this back to a res. Res is equal to this. Okay. We return our res. We fix this. We don't need to append a tuple. Okay, let's get rid of that. Let's do res.append. Code.copy. Alright, we got our code total. Instead of checking this, we check our code total, right? Code total. Code total, right? Okay. Instead of doing this recursive call here, we can do for, okay. For I in range, we go from start to the length of candidates. Okay. That means we can get rid of this code.pop. Append our value. We have our index here, right? Then we backtrack with our index. Ooh. Cut up pop. There's +1 cut up pop. We go from our start. Okay. Oh no, we want our I. Whoops, not our. Okay, so as we loop, right, we're going to go into this backtrack and we're going to start from 0. Okay. Right. We're going to go through here. We're going to go for I in range start to length candidates, right? So we're going to 10 here. We're going to append the 10. Then we're going to backtrack to I +1. Call it again. Total. Total plus candidates I. Okay, so we're back here. So now how would we prune this? Okay, so we can check, well, if code total is greater than target. I guess, yeah, it would be plus candidates I is greater than target. We can break here, right? If I is greater than start. I +1. Okay, we're looping through. We're checking if I is greater than start. Candidates I is equal to candidates I -1. I don't understand. This is quantization, so. Same combination, just pick different ones. It's too big. Right, this one here cuts off, sorry, avoids duplicates. But I don't understand, I understand that this if statement, I get this, right? Because it's sorted, and after that, you know, you're guaranteed that the next number is going to be bigger. But I don't understand here is how this avoids the duplicates. If I is greater than star and candidate's I is equal to candidate's I minus 1. Like, how does this avoid the duplicates properly? This loop inside of this star path. I is equal to 0 is equal to 1. Add 1 to path 1. Start is equal to 1. Path 1. I is equal to candidates 1 is equal to 1. Okay, not skip because I is equal to start. Start 2, path 1, 1. I is equal to 4. I still don't really get it, man. pulling here, man. Alright, so start at level 0, pick candidate 0, path 1, total 1, backtrack 1, 1. Okay, pick candidates at 1, 1, 1, total 2, right? Backtrack 2, 1, 1, 2. Okay, pick 2, 1, 1, 2, right? Pick 5. Just start to link candidates avoid duplicates if I is greater. Bro, why is this so tough for me to wrap my head around, bro? Like, maybe if I just draw a recursion tree here. Alright, so we start at... Okay, do we have a smaller example maybe? Like... Let's do this one. We have a smaller example, right? So we start our recursion, right? And our recursion starts at 0, empty string, 0, right? We enter our loop, we go for I in range start to length candidates, right? So we start at 0, okay? None of this stuff applies here. So we append cur, right? So our first value is we'd append to our thing, right? And then our total would go up to 2, right? And then we call the backtracking function, right? I plus 1, so we go to 1 now, right?
our total is 2, and our candidate's cur, right? 2 plus candidate's I is 2, right? So now we're in the next loop. We go through, okay, we do, well, if cur total is greater than target, no, it's not. If cur total is equal to target, well, no, it's not. For I in range start, right? We start at 1, okay? Then we check, okay, well, if I is greater than start, it's not, because I starts from 1, right? None of this shit applies, none of this shit applies. We'd append our next value, right? 5. Okay, so now we'd be at 2, 5. 2, 5. This would be at 7 now, right? And we'd go to our next value, right? So now we're at 2. Right? We go back to here, none of this shit applies. Oh, our target is 5. Oh shit. Okay. I think we'd still call this function. Yeah, we'd still call this. Alright, go right next value. We'd see, okay, it's greater than target, so we'd return, right? So we'd return back to our previous call where we were at 1, right? Actually, no, we'd do plus candidate's I. We'd break before we'd even get there. Oh, shit. Okay. Well, okay, we wouldn't even enter this backtracking loop because we'd see that the next value here is I, so we'd break, right? So we'd go back to 0, right? We'd be back at 0, and we'd check, okay, we'd probably want to check 2, 2 then, right? 2, 2 is less than, oh shit, we're not ordered, dude. Oh my god, dude. Okay, I'm gonna refix this. Okay, so we're at 1, 2, 2, 2, 2, 5, right? This is our sorted array. Okay. We'd start off at 0, right? Append 1, right? Then we'd call our function I plus 1. So now we're here, right? We start off at 0, empty string, 0, right? Now we're at 1, and we've got 1 inside of here. And we're at 1, right? We go through here, and we go, okay, for I in range start length, we'd start at 1, and we check, okay, if I is greater than the start, well, no, it's not. If go total plus the next candidate's I is greater than target, we'd break. Well, no, it's not, right? Target's 5, so we'd append 2, right? So now we'd append we'd append 1, 2, right? So we're at index I, we're at 2, and we'd append 1, 2, right? And we'd be at 3 now. Okay. We go through this next loop. We do the same thing. We get back here, and we append candidate's I, right? So we'd append. We go to 3, and we'd append 1, 2, 2, right? This would be 5. Okay. So then we enter this loop here. See that the target is equal to that. We'd append to res, and then we'd return, right? So we're returning to that. We're returning this function, right? So we'd append this, right? We'd append this over here. Then we'd return back to our previous function call, right? So we'd get rid of this, right? And we'd return back to here, right? And we'd have 1, 2, 2. Sorry. 1, 2, 2 over here, right? We'd come back here and we'd do, okay. We'd code our pop, right? So we'd pop from here. And then go to our next value, right? So we do, all right. We did 1, 2, so we'd append 2 again, right? We keep doing, I mean, this recursion call is going to go forever, but I think I understand, right? And then if we go, well, if I is greater than start, candidate's I. Okay, right. So we're doing the I is greater than start because now we're greater than start, right? Because now we're actually inside the for loop and we're looping. So now our I is greater than start. And candidate's I is equal to candidate's I minus 1. So we have a duplicate, right? So here, it would stop us. Right, we have 1, 2, 2. We've seen this before. So we'd break from here. Okay. It's a little bit of a harder way to think about it. I definitely would not have got it, but man, it's tough to think about that, but we spent way too long on that problem. Let's jump to our permutations problem. We have solved this one too. Given an array of nums, distinct integers, return all possible permutations. You can return the answer in any order. Okay. Alright, so obviously we can see from here that the base case here would be, well, def backtrack, we put in our, I guess we'd start at 0 and cur as well. That'll index and cur. Our base case here would be, well, we need to compare. Well, if the length of cur is equal to the length of nums, right, then we would simply res.append cur.copy, right? We'd return here. We need our res array. Okay, then we have our recursive case, right, where we go, all right, we need to cur.append nums index, right? Then we'd want to increment by 1, right? So we call our function, backtrack, increment our index by 1, pass in our cur, right? And then obviously we'd probably need to pop, right, to our next element. And then backtrack our index plus 1, cur. We'll return our res. Oh. Darling. Turn res. We're not even calling our backtracking function, that's why. Backtrack. We want to start at index 0, start at an empty. This index is out of range. Well, we'd have to check if you're in range. Well, if the index is less than we need to allow duplicates. An array nums of distinct integers, return all possible permutations. You return the answer in any order. All the permutations.
Indentations. Well, we need to edit this. I mean, we got the base case. We need to know if the length of that is the same, right? So how can we loop through this? See, it's backtracking. Okay, well. Code auto append. Index, right? Code auto append. And we call our backtracking function. Backtrack index plus 1. And then we'd have to check, okay, what would be our next value here? Well, how are we going to be able to pop all the way back? That's the issue. We're going to need some sort of for loop or something. Right, I feel like we need some sort of for loop. Next, maybe a start or something. We go, okay, for I in range start to the length of nums. I have to do, okay, well, the first thing we need to do is we need to append to code auto append. We append our num start, right? This is tough, bro. Okay. Wait from start to length nums. Bro, dude, this is so tough, bro. How can we loop through this? If we append our value, right? We append our value. Then we can somehow append. We go here. We call the next value. backtracking. Oh my god, dude. Man, I'm gonna need to look at another backtracking video, dude.
Hey everyone, welcome back, and let's write some more Leetcode today. And don't forget to like the video, it supports the channel a lot. Today, let's look at Leetcode 46 permutation. And this is more of a math problem than it is actually like a coding problem, which makes it kind of difficult. So we're given an array of numbers, a list of distinct numbers, and we want to return all possible permutation. And lucky for us, we can do that in any order we want. So in the first example, we have 1, 2, 3. Every single permutation is listed. Every single permutation is unique as well. Now, what even is a permutation? If you look at this array, it has 3 values, right? 3 unique values. How do we know how many permutations we can even make from that? Well, it's a math problem, right? So we have 3 positions. We know that in the first position, we can pick any of these 3 values. So we have 3 choices. In the second position, since we already chose one of these values, now we only have 2 values left. So in this position, we can pick 2 values. In the last position, we know there's only 1 value left remaining, so we do that. And so it's 3 times 2 times 1, so it's 6 permutations that we can make, and looking at the result, there are exactly 6. So that's a little bit of like the math background. If you want to solve this problem on pen and paper, it's actually not that bad, right? Because let's say we have like a decision tree type thing. In the first choice, if we're picking the first value, we have 3 choices, right? We can pick 1, 2, or 3. In the second, if we pick a 1, then we can't pick a 1 again, so we can pick a 2 or a 3. Lastly, if we picked a 1 and a 2, then we can only pick a 3 here. Here we can pick a 2, and I'm going to repeat that for the other examples as well. And lastly, we picked a 3, a 1, so we can do a 2 here. And here's the opposite, we can do a 1. So this is the decision tree, but how does this help us? If you notice, these are the permutations, right? 1, 2, 3 is the first permutation. Next, 1, 3, 2 is the next permutation. And we could just keep doing this all day, right? 3, 2, 1 is the last permutation. So solving this problem on pen and paper is actually not that bad, but writing the code to do it is a little bit more difficult, and I'm going to show you the algorithm to do that. So initially, we have our input array, right, with 3 values. The first thing I want to do is say, okay, let's say I got rid of this 1 and I just want the permutations of these 2 values. Then I can go down my decision tree down here, and I can now start getting all permutations of 2 and 3. So I took this big problem, right? We had 3 values here. I took it to a sub problem where now we only have 2 values. And I want to take it one step further. We have 2 values. I'm going to get rid of this 2, And now I want all permutations of this 3. So I'm going to go down my left the left subtree one more time. And now this is the base case. Clearly we can't really go any further. There's nothing left. All permutations of 3 are just going to be 3. So now we're actually going to go back up our decision tree. This was the base case, right, with just 1 3, and we got rid of the 2, remember? So we have to add it again. So we'll add it to the end of this list. So it's a little messy visually, but the new list is going to be 3 and 2, right? So that's one permutation of 2 and 3. So I'm just going to put it over here, 3 and 2. And we can repeat that process. So we already looked at this case. Now we want to look at the case where we find all permutations of 2 so we can get rid of this 3. And then we're going to go down our right subtree. And again, we get to a base case. So we're done with this value. And so in our code recursively, we're going to go back up. And we're going to remember that we removed the 3, so we're going to add it back to our list. And then you can see we have 2 values in our list still, 2 and 3. So I'm just going to put that down over here, 2 and 3. So these are the 2 permutations we got with these 2 values. And one more time, we're going to return back up. We remember we removed this 1 as we were going down our left subtree, so to each of these 2 lists, we're going to append a 1. We're going to add it to the end. So a 1 here and a 1 here. So now, so far, we found 2 permutations. We can add that to our result now. So one permutation is 3, 2, 1, 2, 3, 1. So this is like the main idea. This is what we're going to be doing as we repeat the process for these other subtrees, and then recursively as we compute like the sub problem, as we get permutations of smaller and smaller lists, we're going to take those permutations, return them back up to the result, and then we're going to add them to our result here, and at the end we should have 6 of them, and we can return that. Okay, so now let's write the code.
That was such a confusing example, man. Like,
I'm gonna do this recursively because it's like a backtracking solution.
Watch this instead.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem. Permutations. I've actually already solved this problem before, but I think I could explain it a bit better, so I wanted to do it again. We're given an array of distinct integers, and we want to return all possible permutations of those integers. So for the record, a permutation of a set of numbers like this would look something like this. We have 3 numbers, so we're going to have 3 positions to fill. For the first position, we have 3 choices. We can pick any of these 3 elements. So let's put a 3 over here. For the second position, we don't know which element we already picked. We could have picked this one or this one or this one for the first spot. But either way, we know we're going to have only 2 elements remaining to choose from to place over here. So there's going to be 2 different elements that go here. And then after we've picked the first 2 elements, this one is already decided. So we'll put a 1 here. So 3 times 2 times 1, we'll have 6 different permutations of this set of numbers. And in order to visualize it, let's kind of draw a decision tree. So let's say that for the first choice, we can choose among 3 elements. We can have 1, 2, or 3. So regardless of which path we take, we're going to have 2 choices. Here we can have either a 2 or a 3. We can't have a 1 because we already picked it. Here we can have a 1 or a 3 because we can't have 2. We already picked it. Here we can have a 1 or a 2, but not a 3. So now it's going to get a bit more simple. We'll only have one choice for each of these, and it must be the element we haven't chosen. So here it's going to be 3, here it's going to be 2, here it's going to be 3, here it's going to be 1, here we haven't chosen 2, and here we haven't chosen 1. So now, if you go through each path, we have a permutation. We have exactly 6 of them, and you can see every single one of these is different. So if we could have each of these in an array, this is the result. Like, we've calculated the entire result. Now, the only problem with the way we're thinking about it here is it's pretty easy on like pen and paper to draw this out, but how would we actually calculate this in terms of code? Obviously, it looks like we're using recursion, and it's definitely possible to do it that way, but the way we're doing it right now involves a decent amount of bookkeeping. Because what exactly is the subproblem? Like here, we chose 1, right? So we got rid of 1, and these are the elements remaining. So now we're trying to create permutations with those elements. But here, the subproblem is different. Here we use 2, so now we have these elements remaining, and we're trying to create permutations with those elements. Again, we could do it this way, but it would involve like removing this element and doing some other stuff. So I think a slightly easier way to think about this problem is to really use the idea of subproblems, because it makes recursion very, very easy. So let me kind of redo this in a very simple way. Now we're still gonna use recursion, but we're actually not even gonna branch anywhere. So you're gonna see something interesting. Here, we have 3 numbers to choose from. So what we're trying to do is give me all permutations from 1, 2, and 3. But next, the subproblem we're gonna ask is this: give me all permutations with just these 2 numbers. So we're going to have something like this, 2, 3. And then finally, we're going to ask, just give me all permutations with just a single number. Notice how it's getting more simple as we go down. So watch what the return value is going to be. Well, first, let's go to the base case. If I don't have any elements, from here, I'm going to return up an array with an empty list. Like, that's our permutation. We can only create one permutation with an empty set of numbers, and it's an empty permutation. So that's the base case, just to keep it simple. And now it's going to stay pretty simple. With just 3, how many permutations could we have? Well, it would look like this. We're going to return up to the parent just a single array with the value 3, because a single number can only be permutated like that. Now it's going to get more interesting. From here now, from this subproblem 2 and 3, how do we solve it? Well, you probably know what the return value is going to look like. It's going to look pretty simple, just like this. So it's going to have 2 in the front, and it's going to have 2 in the back. So 3, 2, like this. So these are the 2 permutations we can create. Now, the reason I'm showing you this way is so easy to calculate. Just watch this. From the base case, all we do is just add 3 to that list. Okay, now from here, this was the numbers we're given. We already got all permutations from 3, so now the only thing to do is to add 2. So what we do now with this array, it's a very simple array, it just has one element. So we know we have 2 choices actually. With 2, we can put it at the front, or we can put it at the back. So that's exactly what we do. We create a permutation with 2 at the front, and then we create a permutation with 2 at the back. And then from here, we're going to do the same thing. We have these 2 permutations, 2 and 3. What we're going to do is try to put 1 in every position. We're going to try to put 1 at the beginning. We're going to try to put 1 in the middle. And we're going to try to put 1 at the end. So we're going to end up with 3 different permutations. We're going to do the same thing with this one. We also have 3, 2. It's obviously different from 2, 3. So we're going to put 1 at the beginning, in the middle, and at the end. And if we do this, we're going to end up with 3 more permutations, which is 6 total permutations. And that's obviously going to be the result. And if you're curious, I'll quickly draw out those permutations. Here, 1 goes at the end. Here, 1 goes in the middle. When I said end, I meant beginning, sorry. Here, 1 goes at the end. And from this permutation, 3, 2, we're going to put 1 at the beginning. So 1, 3, 2. We're going to put 1 in the middle, 3, 1, 2, and we're going to put 1 at the end, 3, 2, 1. These are the 6 permutations. Now let's code it up, and I'll also explain the time complexity in the coding solution. So we're going to start with the base case, which is pretty simple in our case. We're going to have the length of the input, and when it's equal to 0, we're going to return a list with a single empty list inside of it. And so the reason we're using that is because we're only going to have a single parameter, the input list. The idea is that we're going to keep calling the recursive function with the input nums without the first element. So that's the sub problem. Just get rid of the first element from nums, just create a subarray starting at index 1, and that'll give us all the values from nums except the first one. So these are our permutations, like our sub problem, and then we want to, from these, add the current element, which is the number at index 0, to all of these in every possible position. And we're going to store those in another variable, which I'm going to call result. That's what we're going to end up returning from this function. Now, to actually do what I said earlier, let's just go through every single permutation that we have. And for each permutation, let's go through every possible index that we could insert the current value into that permutation. So I'm going to get the length of p. I'm also going to have +1 because we technically could add to the end of the permutation as well. So now for that permutation p, I'm actually going to create a copy of it because we're going to use this one multiple times. We're going to possibly add a value to it in multiple different places. We don't want to modify the original permutation. We just want to create a copy of it. So I'm going to store that in a variable called pcopy. Then for pcopy, we want to insert at index I the value nums at index 0. We're taking this value, inserting it at this index. We're going to do that for every index, and then we're going to take pcopy and append it to the result. We're going to do that for every permutation, and then the result is going to be here, and then we're just going to go ahead and return. Now, as you can see on the left, this solution works, and it is very efficient. Well, it's about as efficient as we can get for this problem. And let me just kind of show you how to analyze the time complexity. The idea here is it's going to be easier for us to do it without kind of focusing too much on the code. Remember that how many permutations are we going to have? Well, if we have 3 elements, we had something like 3 times 2 times 1. That is a math equation called n factorial. So if we have n elements in the input, we're going to have this many different permutations.
Oh, bro. What an interesting way to solve this, dude. Ryzen cur, backtrack function. If it's like we append cur, recursive for I in range length nums. If nums I in cur, we continue. Cur or append nums I. What an interesting way to think about this problem. How did I come up with this solution, bro? Like, the solution's goated, dude. Bro, this is such a beautiful way to think about the problem, dude. Like, okay, let's check. Well, if nums I incur, then we just continue. Cool. Pop. Jeez, man, what a beautiful, concise solution. See, I feel like this solution is much easier than this one, right? Like, in this one here, I mean, if length nums is equal to 0, right, we return this. Okay, we found stuff times 1. Like nums. Nums I incur, we continue, right? So we would append cur straight away, then we call backtrack, right? We backtrack at our current value, we'd loop through again from 0, right? From the beginning of the array, we'd loop through and we do, okay, 1's in there, we would just add 2. Go through here, we append 2, we backtrack, right? It's such a beautiful way to think about this problem. Like, all right, we're gonna call it here for the day. Appreciate you guys watching. We'll get back at it tomorrow. You know, I just it's so frustrating sometimes when you come back to this and you're not sure how to solve it. It's just like these little tricks, like it's these little intuition, like, oh, okay, like, you know, we can keep a cur array, we can do this, you know, like it's just very very tough to think about it, you know. Yeah, we go back to like combination sum 2. And it's like, bro, like, All right. We'll get back at it. Just being consistent, we'll get better. So appreciate you guys watching. We'll see you tomorrow.